So now let's cover an example problem that you might see for a matrix. And surprise, surprise, the algorithm we're going to use is DFS. I told you it's one of the most common algorithms, and that's because it's very, very frequently applied to graphs. So in this example, we have pretty much the same matrix we looked at earlier. We want to count the unique paths starting from the top left and going to the bottom right. In this case, of course, the path can only move along zeros, not on any ones. And also, for a single path, we can't visit the same cell more than once. Why is that important? Well, take a look at this. We can go along these zeros, and then we could go down here and then left here, and then we could pretty much be in an infinite loop over here. Among these four, we could basically keep going in a circle and however many times we want to, and then we could move down and then get to our destination, the bottom right. So in that case, what would be the answer to this question? Well, it would basically be infinity, and that's kind of boring. So we don't want to, for any single path, like suppose we go here and then we go down and then we go to the left. Now we can't move to this cell because we've already visited it, and we can't move to this cell because we've already visited. So the only option we have here is moving to the left. We can't do that. It's blocked. So we can only go down. Now here, of course, we can visit a couple cells that we haven't visited before. We can't go to the right. It's blocked off. But at this point, you probably get the idea. So when we want to count the paths, we want to go through every single possibility. So an algorithm like DFS is going to be helpful for us. This also might remind you of backtracking, which is what we talked earlier, and that's because it pretty much is. This is an example of backtracking. There's a big overlap when it comes to DFS and backtracking. They're both recursive and they're both very, very similar in nature. So this DFS is definitely going to be more complicated than when we looked at binary trees. So I'm going to just show you the code immediately, and we're going to see how in general the algorithm will run visually and then compare that to what the code would do. And by the way, yes, again, this is going to be a recursive algorithm with the recursive case and of course a couple base cases. In this case, we don't just have one base case, we actually have two. Now, the simplest way to think about this is not to immediately look at the code, but to think about it visually. It's all a matter of choices. We start at the top left. Like that's always where we're going to start. So in terms of the parameters that we're going to be given the grid, of course, that's our two-dimensional matrix here. We're going to be given what's our starting position. In this case, it's going to be 0, 0. So we can have kind of the dimensions written out. So we're starting at the top left. And what are our choices? Well, remember, we can move in all four directions. We can move up, we can move left, we can move down, and we can move right. And we know that's going to be kind of annoying because we can potentially move out of bounds. That's the first thing that we have to worry about. So that's what the first base case is going to be. First of all, here you can see I'm getting the dimensions of the grid. This is how you would do it in Python. So the length of the grid, which is going to be this, is going to give us the number of rows that we have. The length of one of these rows, you can see I'm just taking the first row because we know every single row is going to have the same length because this is a rectangle. I think it's safe to assume that most of the time. And the length of one of those rows is going to be the number of columns. In this case, we have a simple case because we have a square matrix, so it's 4 by 4, but that might not necessarily be the case. Now, in my case, I'm calculating this every time we call the function. That's pretty unnecessary to do. We could pass in those parameters to the function, but I prefer to do it this way because it gets kind of annoying when you have to pass in 6 parameters into a function. But it doesn't change the time complexity, so this isn't such a big deal. The important thing is we have the dimensions of the matrix. Now, one case is that our row, remember this is the row, goes out of bounds. It's too small, or our column goes out of bounds. So what we could check is our row less than 0, or is our column less than 0? Or you could simplify that into a single case because the minimum of these If the minimum is less than 0, that's all we care about. We just care about if one of these is too small. So we can just take the minimum of the row and the column and check, is it less than 0? That means either this is too small or this is too small. It doesn't matter because we're out of bounds either way. What would we do if that was the case? Well, if we end up going out of bounds, that clearly means that we did not find a path, at least down this recursive, chain, this path, we did not find a path to the destination. So in that case, we would return true. This DFS is supposed to count the number of paths. You can see that there's a few more cases where we would return 0. I'll get to those in a minute, especially as we run through the example. But to briefly cover them now, another case, of course, for our row and column, instead of being too small, they could be too big. Our row could be equal to the number of rows. Why are we checking if it's equal to the number of rows instead of greater? Well, remember, the number of rows is going to be 4, not 3. We have 4 rows. The last index is 3, but the number of rows is 4. So if row ever goes out of bounds, if it ever equals 4, then we also return 0. Or if our column goes out of bounds, it reaches 4, then we also return 0, right? We did not find a path. We went out of bounds. Why can't we take the max of the row and the column and check if it's greater? Well, because remember, the number of rows and columns might not necessarily be equal. In this case, since they're equal, we could take the max of the row and the column, but maybe if we had 4 columns, we would not be able to do that. We know we go out of bounds this way or this way if we're less than 0, because that's always going to be the starting point, but the ending point could be different. That's another case where we would return 0. And another case would be, this is the slightly more simple one, is if we reach a blocked position. Like from here, right, starting at the top left, we go down, well, we reached a blocked position. We're not even supposed to be here. So we basically stop searching. We're not going to continue our recursive case because we're not allowed to even visit this position. So we're going to stop immediately, and we're also going to return 0. Basically, we're saying by visiting this position, there are no valid paths that reach the destination. So again, we return 0. Now, the other case is if we reach a position that we've already visited before. And what is this visit actually going to be? Well, it's going to be a hash set data structure. So that's what we're going to end up passing in. It's not super clear in Python because we don't have static typing, but this visit is going to be a hash set. And it's going to tell us if we visited a position before along a given path. So that would be the example where we go here, then we go down, then we go left, and then maybe we go back up to the same position. At this point, if we visited the same position twice, we would stop. We'd say, nope. If we visit this position twice, there are no valid paths that reach the destination. We're not allowed to do this. So we return 0. The other base case is, of course, we end up somehow reaching the bottom right. We reach the destination. How do we know we reached the destination? Well, it's defined as the last row and the last column. So if R is equal to the last row, which is row minus 1, and our column is equal to columns minus 1, then we return 1. That means we found a single path. This is that particular path, for instance, right? This is one path that could be counted as part of the solution. Now let's actually run through this example and see how the code would actually execute. So when we actually call this function, our DFS, we're going to pass in the grid, of course. We're going to pass in 0 as the starting row and 0 as the starting column, and we're going to pass in some hash set. And that hash set is going to be reused throughout this recursive function. What that means is we're not creating a new hash set every time we make a recursive call. We're passing in a reference to that exact same object. Every recursive call is going to have access to that exact same object. So starting at the top left, we're going to, run through our base cases. Have we gone out of bounds? No, we haven't gone out of bounds. Have we already visited this position? Nope. Is this position blocked? Nope. Let's assume, by the way, there's always going to be at least one valid path in this matrix. But if you're not sure of that in a real interview, it's worth asking that as a clarifying question to your interviewer. Next, let's check maybe we've already reached the destination. No, we haven't. We can't return. So at this point, what we're going to do is add this coordinate to our visit hash set. The reason I'm using a hash set in this case is because it's just easier in terms of code. to just add a pair of values to check if we've done this before. And we know adding and removing from a hash set is going to be a constant time operation, but alternatively, you could use a two-dimensional grid. Like visually, what I'm going to do is basically just mark the positions that we've already visited with a blue circle. So if we wanted to know if any of these positions is visited, we could use a hash set, or we could use a two-dimensional grid of the same size as the grid to represent that information. If you're allowed to modify the grid, you could also, as you visit a position, mark it as a 1 to indicate that it's already been visited, because then logically we will basically assume that we can't visit that position. But it's not always safe to assume that you can modify the input grid, so we're going to ignore that for now. So now that we've added this to our visit hash set, it's time to do the recursive case. We're going to set our count equal to 0. We're basically saying that from this position, we want to count how many ways we can reach the result. And we're allowed to move in 4 directions. So we can move down, that's going to be row plus 1. We can move up, that's going to be row minus 1. We can move to the right, that's going to be column plus 1. And we can move to the left, that's going to be column minus 1. Now, when we go up, we're going to go out of bounds. Our row is going to be less than 0, so we're going to end up returning 0. Okay, what about when our column goes to the left? We're going to end up returning 0. What about when we go down? Well, in that case, we're going to visit a blocked position. So in that case, we're going to return 0 again because it's blocked. So the only valid position we can go to is to the right over here. And when we do that, we're not out of bounds. We haven't already visited this, and it's not blocked. It's also not the destination, so we can't return 1, but we are going to add it to our visit hash set. So far we've visited these 2 positions. Now that we've gotten an idea of how the base cases work, I'm going to start running through them a little bit quicker. So from this position now, this second position that we're at, we're going to have another count variable. We're counting how many ways from this position can we reach the destination. And when we find that result, we're going to return that to the previous position that we were at, which was the starting position, and then we're going to have our answer. Basically, these two are going to have the same count. Now from here, we're allowed to go in 4 directions. We can go up, can't do that. We can go to the left, that is valid, but it's already been visited. We know that because it's blue here, but we know in code we would add it to our visit hash set. So it's already been visited, we can't do that. So we can go down, well, we can't do that either. It's already blocked. So we can't visit this position. So we can only move to the right. And then from here, this is valid. Neither of the base cases are going to execute. Now, from here, we're also going to have a cost, which is initially going to be 0, but when we calculate it, we're going to end up returning that cost to the previous node, which is going to end up returning its cost to the previous position. But from here, we can go in 4 directions. We can go up, it's out of bounds. We can go to the left, it's a position we've already visited, but we have 2 valid positions now that we can go to. We can go to the right, or we can go down. Now, since this is a DFS, depth first search, it's recursive, we're not going to go along these 2 paths simultaneously. We're only going to do one at a time. We're going to go as deep as we can in one of them, and then we're going to go backwards. We're going to backtrack. That's why this is a backtracking algorithm. And then we're going to go back to where we were, and then we're going to go along the other path. So in terms of code, which one of these would execute first? Well, it looks like row plus 1, which is this one, would be first. So let's just go along that. So this is going to be added to the visit hash set. And then from here, neither of the base cases is going to execute. This is going to be added to visit. And now we have 4 choices. We can go up, can't do that. It's already been visited. Can't go left, it's blocked. We can go to the right here, and we can go down here. Which one of them is going to execute first? Well, as we saw before, down is going to execute first. But just to actually quickly run through the other case, what would happen if we went here? Well, then we don't have many choices. We can't go to the left. We can't go to the right. We can't go down. We can go up here, right? And then when we go up here, we'd be stuck. We can't go to the left. We can't go up. We can't go down. We can't go below because it's already been visited. So this path, essentially what I'm saying is, would not lead us to a solution. So let's keep that in mind. But going down here, it's also not a base case. We have some choices, can't go up, can't go to the right, but we can go left and we can go down. What's going to happen, by the way, if we went left? Well, here we wouldn't have many choices. We could only go to the left one more time. And here we can only go down. And here we have 0 choices. We haven't reached the destination and we can't move anywhere else. We can't visit the same positions we've already visited. So we'd be trapped, and along this path, we would end up returning the base case 0. Okay, so the question remains, from here, can we even reach the result at all? Can't go to the right. Well, we can go down. So from here, the only valid choice, as you can see, is moving to the right recursively. And at this point, we would finally execute the base case where we have reached the destination. And then we would return 1. So from here, this cell, we would have a cost of 0. We would execute 4 DFSs in all 4 directions. 3 of them would return 0. This one would return 0, this one would return 0, and this one would return 0. But the one here, the one where the column is incremented by 1, would return 1. And at this point, we would end up returning 1 to the previous node. But before we return 1 to the previous node, you can see we're backtracking. First, we marked this position as visited, and now we're going to mark it as unvisited. You're going to see why we're doing that in just a second. So from here now, we're going to backtrack. We're going to mark this as unvisited and go to this node. From here, we know that there was only one path here that led us to the solution. So from here, the count would also be 1, and we would return 1 to the previous node. And before we do that, we'd mark this as unvisited. So then we're going to go back to this node. We know from here, only one of the paths reached the destination. So from here, we would return 1 to this node. Now this node, if you recall, had 2 choices. We could either go down, which we just talked about right now, or we could go to the right. Now from here, we're going to go to the right. We're going to execute the second valid case. But now, as you can see, all of these are marked as unvisited. Why is that allowed? I thought we could only visit the same position once. Well, that's only true along a single path. What I'm getting at here is we could from here have 2 paths. We could, do something like this that reaches the destination. But we could also have a path like this that reaches the destination. These are 2 different paths. So they are allowed to visit the same position, right? Both of the paths visit this position, as you can see, and this position, and this position, and even the result. I mean, of course, they have to both reach the result. We said only a single path can't visit the same position twice, but multiple paths can reach the same position. In fact, they have to if they want to both reach the result. So I hope that makes sense. It can be a point of confusion. But as you can see from here, we don't have many choices. We can go down, and then we can go to the left, and then we can go down. And then from here, we're going to end up trying this path. It's not going to reach the result. And we're also going to try this path where we go down and then to the right. And again, we are going to reach the result, but this is a slightly different path. This is a slightly longer path, but it's still valid. So what we would realize then is, backtracking all the way back, is from here, we can reach the result in one way. From here, we can also reach the result in one way. So what that means is from here, we can reach the result in 2 ways. And what about from here? Well, from here, we're going to end up returning the count back to this. So we're going to say that from here, we can also reach the result in 2 ways. And we're going to return that to the previous, which is here. And we're going to say we can reach the result from the starting position. We can reach the destination in 2 ways. And that's going to be the final value that we return. So when we call our DFS with these parameters and then print the result, 2 is going to be the value that we print. You can try it in any of the code languages that we provide. So now finally, when it comes to analyzing the time complexity of a solution like this, it can get pretty complicated. So I like to think about it in a simple way, but it's not super precise. I mean, the way I'm going to think about it is just by proving to you the big O of n boundary, but it's not going to be super precise. We know from the starting position, let's suppose that the worst case is where there's all zeros. We don't have any blocked paths. So in that case, the length of a path could be the size of the matrix, right? Any given path could be the size of the matrix. So thinking about it in terms of a decision tree, we have, from any position, we have 4 choices. And for each of those positions, we have 4 more choices. And by 4 choices, I mean we can go left, right, up, or down. Now, of course, we know some of them are going to execute the base case where we either go out of bounds, or maybe we visit the same position twice, or we visit a blocked position. But like I said, this is an imprecise way, but it still gives us an idea of the upper bound. For every node, we're going to have 4 choices, and the height of this tree is going to be the size of the matrix, because we know the longest path, which is what this tree represents. This tree represents a given path. Like if you follow a path in this tree, it represents a path in the matrix. So the height of the tree is going to be the number of rows times the number of columns. Now, if you recall from our binary tree analysis, this is going to be basically the number of branches, which in this case is 4, raised to the power of the height of the tree, which is r times c. More commonly, people will, use the dimensions to mean n times m. So you could say that the time complexity of this is going to be 4 to the power of n times m. That's the big O time complexity. So this is not very efficient, but that's expected when it comes to brute force DFS backtracking. Now, the memory complexity would essentially be the recursive call stack. That means when we start at this position, then we make a recursive call here, then a recursive call here, and do that for pretty much the entire size of the matrix. At most, there could be that many recursive calls outstanding at the same time. So we say that the memory complexity is going to be n times m. We could also say this is the memory complexity from our visit hash set, because that is also going to be the size of the grid. Or instead of having a hash set, you could just create a grid itself to keep track of visited positions. So that's the idea here. I know it's pretty complicated. It's not the type of thing you'll completely understand the first time you see it. It can take a while to wrap your head around a lot of the concepts that we talked about here. But DFS, especially on a matrix, comes up quite often. Check out the practice section for graphs if you want to find some practice problems that you can try out.